it was to toggle between X's and O's for the player and just let them make moves indefinitely. So if I go ahead and run this, just so we remember what we did last time, we have it so please enter a row. So we're going to go ahead and choose, do we do row 0, row 1, row 2, or row 1? We did row based on row 1. So we'll put in a 1. Please enter a column. We'll do a 2, and that should put it in the middle on the top row. Okay. So we want to make that so that it happens indefinitely. So that's we're repeating something. That should be inside of a loop. And for right now, we'll just have that loop last forever. So while true, we're going to ask these same questions. Enter a row, get information, enter a column, get information, and then we'll make the move, assuming an X for right now. So we'll go ahead and paste that in there. All right. Okay, so now it's going to ask us over and over again, allowing X to make a move over and over and over again. We're not toggling between players yet. Oh, well, we need to actually call upon this. So after we call main, we need to tell it to go ahead and play the game. Oh, and like I said last time, driver.playGame. So now our game will start. All right, so please enter a row. 1, 1, 1, 2, 1, 3, so on and so forth. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay, so we can fill our whole board, proving all of our moves are working. But probably don't do like a 3, 4, or it's going to croak on us. All right, because we assume that they're going to give us accurate input. All right, so now we have that asking indefinitely, but we want to toggle back and forth between X and O. So we'll go ahead and we'll say we're going to have a variable. So we need to remember the current move. So again, we're using our memory. So we create a variable. So we're gonna, actually we'll do this as we'll say char cur move is equal to an X. And since now we're storing that X inside of a variable called cur move, we'll go ahead and replace our make move guy here. Instead of hard coding in an X, we'll pass it the current value of cur move. All right. Now, I'm still not making changes to cur move. It's still basically just a synonym for X, but just to prove that this guy still works, we'll go ahead and make a move to 1, 2. There's cur move, so on and so forth. All right, so now after we make a move, though, we need to toggle between X and O. If the last move was an X, the next move should be an O, so on and so forth. So we'll ask a question. If cur move was equal to X, change cur move to be equal to O. Else, cur move is equal to X. All right, so this should toggle back and forth. So after each move, we'll ask the question, was the current move an X? If it was, change it to an O. Otherwise, change it to an X because it must have already been an O. Then we'll loop back up to the while loop. This guy is always true for right now because we don't have a way of checking for a winner. So we're just saying, just keep making moves forever. And we'll ask for information again, and the next move should be an O. So we'll go ahead and hit play. So there's 1, 1, that's an X. 1, 2 should be an O. Well, that's actually interesting.
You don't have a tab after the O in the code.
Oh, thank you. One, 1, 1, 2, 2, 2, 1, 3, 3, 3. All right, so we're toggling back and forth between X's and O's. And we could also overwrite something now in our current version of this, so we're not checking to make sure a move is legal. A homework assignment was just to indefinitely make X's and O moves, but toggle back and forth. So does that fulfill the homework assignment? All right, so before we go any further, let's review the GitHub stuff, since several people had some issues with that. All right, so my code is currently up to date the way I want it to be. So now I want to take that code and I want to update GitHub with it. So this is the same thing we would have done the very first time, except without the git add push or add remote thing, because we only had to do that one time. So I'm going to go to my Git terminal out here. And I'm going to actually just move back to my home directory so we actually have to traverse it. So right now I'm sitting in my home directory here. And if I type in ls, which gives me a directory listing, I do not see the Java files that I'm interested in. I see a whole bunch of other files. Some of them are Java files, but not the ones we actually have as part of our homework. So I need to change directories so that when I type in ls, I see my files. I need to get to that directory. So I'm going to type in cd Dropbox / awesome fat. So what I'm doing here is as I'm typing this in, I say cd Dropbox, I put a slash, and then I press the tab key twice, and that shows me the list of stuff. And then I just start typing the next thing, and I can press tab. That gives me auto completion, so I don't have to just type it in. And then we'll do awesome fat workspaces. So you might as well be typing all these things in. I'm just taking a shortcut to do it. And then I think inside here is my Eclipse workspace. And then there's our folder called TicTacToe. And finally, here's our folder called source. All right, so I am changing directory with CD wherever my source code lives. I need to move to that directory. So wherever that is on your computer, probably a very different path than mine, but a path nonetheless. Okay, so when you press enter there, when I type ls, I see my .java files that I'm interested in. Make sense? All right. So now, in order to add those files, any changes that have been made to my files, I want to go ahead and add to my local repository. So I do a git add dot. Okay, you could also say git add star.java, something like that. But git add dot says add everything that's in this directory. This directory happens to just have .java files in it. So I'll do that. And at this point in time, I have marked all of those .java files for inclusion in my local repository. They're not actually in there yet. I've just staged them to be in there. And I can prove that if I say git status. It'll show me the current status of like that staging. So it's showing that one file has been modified since my last commit, and that is driver.java. All right. And it's been modified. Before, the very first time you do this, it would have said new. Okay, but this guy's been modified. So now I actually want to commit it. So git commit -m, and I need to give it a message. So kind of a little blurb about what this commit was about. So update for homework number, what homework was this? 12. Update for homework number 12. So I did that. So one file changed, 22 insertions, 7 deletions. So basically, I updated my local repository only. GitHub in the cloud has not changed. So Git is the tool we're using. GitHub happens to be a website that knows how Git works. So I can store my stuff in the cloud so it's easy to share. So finally, I need to do the Git Push thing. So I think it's Git -u push origin master. Nah, that's the wrong command. Git push -u origin master. That guy. So git push -u origin master. What that's going to do is it's going to take my local already committed repository that I just finished doing, and it's going to push it to the cloud. All right. So this is where I'm pushing it, origin. And remember, the very first time you set up your repository, you added a remote named origin, and its value is equal to your URL for GitHub. So that's what this guy does. This guy's going to boil down to that remote location, your GitHub link. And then master is the name of your local repository. It just happens to be the name of that guy. So I do that, and now it's going to push it. Tells me everything's cool. The very first time you do that, it'll ask you for your GitHub username and password. All right, so now if I go over to GitHub, notice here we have a new update for homework 12, just this one file. If you click on that, you should see our play game code that we just wrote. Make sense? All right, so that's, again, how the Git and GitHub tools work together. Well, Git is a tool, GitHub is a website. All right, so next step is going to be to determine if there's a winner, right? So we know there's a whole bunch of different ways you can win the game. So let's check for winners. Now, as it stands right now, we are storing our code, or our board, in 3 rows. So we can have a winner across row 1, a winner across row 2, or a winner across row 3. We also probably want to govern them only being allowed to make a move in a underscore, a box that currently says underscore. Okay, so let's do that as part of our update to our play game. So when they enter in a row and column, before we just allow them to haphazardly make a move, we want to check to make sure they're allowed to make a move there. And they're only going to be allowed to make moves in areas where there's an underscore. And we can actually build that in to make move. So right now, make move returns nothing. We can update that function so that it returns a Boolean, letting us know whether or not a move indeed was successfully made. All right, so we'll go ahead and have make move return a Boolean. Let's go ahead and add in a little comment before this. Returns true if a move was successfully made, and false otherwise. So the very first thing we're going to ask is we're going to ask if row column is a legal move. Let's keep assuming that it's a legal position on the board. So that way we don't have to say, well, if they enter in a negative number, that's bad. If they enter in a number bigger than 3, that's bad. We won't do that error checking, but we do want to keep them from making a move in a spot that has already had a move. All right, so we're going to ask the question. We want to know if the position row column has a current value of underscore. If it has a current value of underscore, we're allowed to do a move. If it has something else, which would be either an X or an O, that place is currently off limits. Okay, so how does make move currently work? It goes through and it figures out which row you're talking about. So right off the bat, we're figuring out a row. All right, and then this is where we actually make that move right here. So if this first stuff, determine which row array we are talking about. That's what this chunk of code does. It sets the row equal to the appropriate row array that we're dealing with. So now this is what actually makes the move. So before we just make that move, we need to ask the question. If the row that they picked at the particular column that they picked is equal to an underscore, then we need to make the move. So we're asking a question that should set up a red flag right off the bat saying we need to use an if statement. That's how we ask questions. So if the row at position column -1 Okay, and we do column -1 because we decided that our end users will be entering in 1s, 2s, and 3s instead of 0s, 1s, and 2s for the columns. So if that guy is equal to an underscore, okay, notice that again, equivalence in Java is the double equal sign. A single equal sign is the assignment operator. So this will not boil down to a Boolean expression. This is going to try to overwrite the row at bucket column -1 with an underscore. Not what we want right now. We want to ask the question, is this guy equivalent to this guy? Okay. If he is, then we're allowed to make our move. Otherwise, return false. This guy would return true. All right, if it makes you feel more comfortable, you can always put this inside of an else, but the else is not necessary here, because a return statement makes a method, makes a function immediately end. So if we return true here, we will never get down to this line of code. The function ends right here. All right, but if you early on like the syntax of having an if and a corresponding else, it's not wrong. Perfectly acceptable. If this is true, do this crap. If it's false, do this stuff. All right, so ultimately when we try to make a move, we'll come through here, we'll figure out what row we are hopefully making our move in. Then we'll make sure we're allowed to make the move. If we are, we'll make the move and return true. Otherwise, we'll not make the move and we'll return false. So whoever called make move needs to go ahead and look at the result of make move to see if in fact a move was actually made. All right. So we'll come back up here. This is where we're actually making our move. So we are only going to toggle if make move was true. So I could say if make move. So when I called make move, passing it row, passing it column, and passing it my current move, if that guy it boils down to true. If it makes you feel better, you can say equal true. It's redundant because we're going to, if this guy returns true, we're asking is true equal to true. If that guy returns false, we're asking is false equal to true. So it's actually redundant to check to see if it's equal to true. But if you like the look of this syntax better, that's fine. Nobody's getting hurt over it. Okay. Better to write some extra symbols that you understand than less stuff that is confusing to you. But in this case, we'll go ahead and call make move. It's going to boil down to a true or a false. True if it was successful, false otherwise. We'll move our toggle stuff inside. All right, so if the move was successful, we'll go ahead and toggle so that the next time around in our while loop, we'll be making a move for the next guy. Otherwise, if it wasn't successful, we're not going to toggle because that dude needs to actually make an accurate move, like a legal move. All right, in either case, we're going to go ahead and display the board again. We could, if you wanted to give them a little feedback, you could say something like system.out.println illegal move, something like that. And then display the board again. All right, so we'll go ahead and we'll make a move 1-1. And then we'll go ahead and try to make 1-1 again with the O. And it should yell at us. That's an illegal move. It's still O's turn. So now I'll do 1-2, and now we notice O was still his turn. We didn't toggle. We didn't toggle because it was an illegal move. So on and so forth. Make sense? All right. So we are conditionally toggling here. potentially spitting out an illegal move, but always displaying the board. All right, questions about this code as we currently have it written? All right, so at this point we're able to make moves. After each move, we need to determine, well, really, after each successful move, we need to determine if there was a winner. So we'll ask the question, was there a winner after a successful move? Because that's the point when the board actually changes state. All right, so we need to write a method, static Boolean is winner, and it's going to check the current state of the board to see if there was a winner. All right, so initially let's check for horizontal winners. So we're going to check across row 1, row 2, row 3, and see if we have either 3 X's or 3 O's in a row. So, and let's go ahead, I think similarly to how we did this in Alice, as I think we just created several variables and stored the values in. So we're going to say Boolean X winner row 1. Okay, for an X winner on row 1 at bucket 0, 1, and 2 all need to equal X. So this is row 1 at bucket 0 is equal to an X, and row 1 at bucket 1 is equal to an X, and row 1 at bucket 2 is equal to an X. So if all 3 of those things are true, this guy is true. This is double ampersand is the and in Java. All right, and do we have that in our? Let's get down here to our. So under our Boolean operators, we have equivalence. We have not equal to. Now we can go ahead and add in the and the or. That's that. So double ampersand is the and, double vertical bar is the or. Now, something to pay a careful attention to in Java. If you forget to do a double ampersand and instead you do a single ampersand, that is not an error. It is just not doing what you think it's supposed to do. This guy is what's called the bitwise and operator. And this guy is the bitwise or operator. And what I mean by bitwise, let's go ahead and open up Keynote. And by the way, at some point soon, this might be a fun little quiz to do a bitwise and or a bitwise or. If you pay attention right now, it should be a free 100%. If you don't pay attention, like the sleepy head back there, then you might have some issues. So bitwise and looks like this. So for instance, this does things on numbers. So we've already discussed that in Java, numbers are actually under the hood stored as bits, okay, zeros and ones. So a 32-bit number is going to be a stream of 31 zeros and ones for the numeric value, and then one of those bits would be for the sign, right? Okay. Now a bitwise and, similarly a bitwise or, what it does is it compares 2 numbers to each other at the bit level and does ands and ors on each individual bit. So for instance, if we had 1101 bitwise and with 0111, like that, we're going to take this one here and we're going to AND it with this one. So 1 and 1 is 1. So that's true and true is true. So let's actually start on the left. That way you can build it out. So 1 and 0, you can read this as true and false is false. You need to have both sides of an AND true in order to get a true. 1 and 1 is 1. 0 and 1 is 0. 1 and 1 is 1. So the result of 1101 bitwise AND, so this is the actual problem we're solving. 1101 that 0 1 1 1 is equal to 0101. Make sense? Similarly, if we did 1101 bitwise OR was 0111, so this guy is this is the AND. The OR of this is 1 OR 0 is 1. 1 OR 1 is 1. 0 OR 1 is 1. 1 OR 1 is 1. That's the OR. So if there's at least 1 1, it's a 1. That makes sense? So those are bitwise operations. They're actually most commonly used when you need to apply a bunch of filters to something in some language, in some application, let's say. And you have whoever wrote it has created a, let's say, maybe a 16-bit stream of zeros and ones that represent a state of something. Okay, so now you have, and let's say you want to apply 3 different filters to this piece of information, and they have maybe 50 filters, but you're going to apply 3 of them. What you would usually do is take the 3 filters you want to apply and OR them all together, bitwise OR, which will produce this unique new filter that means something. That makes sense? And that's what actually gets applied. It's also used in with the internet with TCP/IP for if you've ever, when you're setting the IP address in your operating system, you see that thing that says subnet mask. You ever seen that word? The thing that says mask? That's actually a bitwise OR of the underlying 0 to 255, which is a unsigned integer, right? Unsigned 8-bit integer would give us 0 to 255. A signed 8-bit integer, a byte primitive type, is negative 128 to positive 127. But if we take the signed bit off of that, that's 0 to 255. So a standard IP address is a byte dot a byte dot a byte dot a byte. That is 0 to 255 followed by a dot, 0 to 255 followed by a dot. Zero to 255, 0 to 255. Or in our world, we might see 192.168.2.14 or something like that. All right, so every one of these numbers will be some number between 0 and 255, which means they're each represented by an unsigned byte. Make some sense? So whenever you see the subnet mask, which is usually something like 255, 255, 255, 0, something like that, what it's doing is it's masking the IP address for security reasons by that, doing a bitwise OR against the IP address and that 255 to give you a, it's called a unique value to uniquely identify that machine on the network, quote, securely. All right. Sometimes you'll also see subnet mask, for which subnetwork they're in on campus or something like that for the IT majors in here. All right, so that's where this bitwise stuff all falls in. But for us in here, from a programming perspective, a single ampersand or a single vertical bar are bitwise Boolean operators to be done on numbers, as opposed to the double ampersand and the double vertical bar are logical Boolean operators to be done on Boolean expressions. All right, so be careful if you get weird error messages when you're writing your code. If you only put in 1 ampersand and you're trying to see if a true is equal to a false, or if you're saying true and you put a single ampersand, it's going to say those dudes aren't numbers, because true and true are Booleans. Where this gets even more cryptic, if we talk about our history of programming languages, in Java, a Boolean under the hood is represented as a number, just like any other language, right? But if you go back to older languages like C, Booleans actually were represented as numbers, zeros and ones. Okay, it was actually 0 and non-zero officially, but it was always 0 or 1 in terms of the implementation. But at that point in time, you technically could do a bitwise AND on 2 Booleans, because the Boolean was actually a number. All right, Java doesn't let you. Java screams at you and says, hey, wait a minute. True is the value of true from your perspective, regardless of how I'm implementing it under the hood, how I'm representing it. If you're saying a true, I'm not going to let you do math with that. Where in a language like C and C++, you could do math with the value of true, because it was just a number. Okay. So, checking for winner, this is whether there was a X winner in row 1. That's if all 3 guys are equal to X. Now let's check for a Y winner in row 1. I'm sorry, Y winner, an O winner. Playing Martian TicTacToe. Or I guess in Big Bang Theory, would it be like Klingon TicTacToe or something like that? Anybody in here watch that show? 3.5 people? That's a good show, isn't it?
It used to be funny.
That's true. But isn't that true of any show?
Yeah.
I mean, were they on season 9 now or something? I mean, they're running out of crap to talk about. Where I get ticked off on there is when they try to be geeky and reference something geeky in real life, but do it wrong. It's like a bunch of times they've done like weird World of Warcraft references and they don't get it right. Like something doesn't actually exist in the game that they claim does. Just in this last episode, and Sheldon gets a new laptop and it has things in it that don't exist in laptops yet, but we're supposed to believe is. Ticks me off. If you're gonna do geeky stuff, get it right. Bring in an expert and make sure that the stuff you're saying is real, right? How long would that take?
You should hire you.
Well, hire somebody. Or heck, just hit Best Buy's website. You know, don't claim that there's a laptop that has a 4K monitor on it when those don't exist at this point. Soon, okay, but the screen size is really too small. I mean, your eyes would have to go Terminator eyes in order for that to work. Okay, we have like 2K laptop screens with the Retina displays or whatever, but you know, just do a quick little pass on Best Buy's website. Look at whatever their most expensive laptop is, and that's what Sheldon got. Those are the specs. Just run those off. Yeah, instead of making up bad things. All right, X winner, O winner on row 1. We'll go ahead and steal those 2 guys. Wouldn't this have been nice to do this in Alice? Just to copy them like that. Oh. Except you got to do it the right way. We're changing the variable names, right? This is row 2, row 2. Row 2, row 2. Row 2, row 2. That's for row 2. This is for row 3. All right, and then we need to do the X winner diag 1, let's call it. So that's going to be Row 1, 0 is an X. Row 2, 1 is an X. And row 3, 2 is an X. Remember, this is Java indexing. That's why it's 0, 1, and 2 there, but row 1, row 2, row 3 for our variable names. And then O, winner, diag1 is 0, 2, 3. And then we have our diag2. All right, row 1, 2, 1, 0, 2, 1, 0. All right, so those are our diagonals. So here's all the different ways you can win in tic-tac-toe. So now we need to return all of these guys ORed together. If at least one of those is true, there was a winner. Go ahead.
You don't have to call it yet.
Oh, thank you. I did the same thing last time, I think, when we were doing this analysis, didn't I? Yeah, I kind of remember that. So here, we'll put them after the rows. So those are the rows. Rows, calls. Diags. So this will be call 1. Call 1. So this is row 2. I'm sorry, row 1, 0. No, row 2, 0. And row 3, 0 is an X. So that's call 1, call 2, 1, 1, 1, 1, 1, 1. And then call 3. 2, 2. 2, 2. 2, 2. There's our potential row winners. Here's our potential column winners. Here's our potential diag winners. And now we just return all those guys ORed together. So X winner row 1 ORed with, we'll do a couple in a row. Y winner, O winner rather, row 1 ORed with, steal these two guys, row 2, row 3, call 1, call 2, call 3, diag1, diag1, and diag2. All right, so this will return winner on X row 1, O winner row 1, X row 2, O row 2, X row 3, O row 3, X col 1, O col 1, X col 2, O col 2, X col 3, O col 3, X diag 1, O diag 1, X diag 2, O diag 2. All ORed together. So if at least one of those guys boiled down to true up here, this will return a true. Okay? So that's our is winner. So now after each move, we can ask, was there a winner? So this is only after a successful move. If this was a successful move, we can check if there was a winner. But why don't we go ahead and check before we change who just made the move? So before we toggle who made the move, let's check if there was a winner. So if driver.isWinner, okay, so if there was just the winner, system.out.println cur_move concatenated with is the winner. And then what we'll go ahead and do is we'll just do a return. Even though play game returns a void, earlier I mentioned that the return keyword immediately makes a function end, immediately makes a method end. Well, methods that have a return type, like this one, Boolean, when we call return, we must then pass it a value afterwards for the value we're going to return. Methods that are void, like play game, this guy's void, he's not going to return anything. This is the return type. When we call return, which we don't have to do, but we optionally can do, we would not pass it a value afterwards. We're just asking the return keyword to effectively kill this function, which does what? It effectively breaks us out of this infinite loop. We never get to this line because we died right here. Make sense? But if you want this to look a little cleaner, we could put this stuff inside of the else. So only do the swap if there wasn't a winner, even though we know that we're never getting to this else if we were in this winner because we died right here. Make some sense? All right. So let's go ahead and run this. A row, so we'll do 1, 1, then we'll do 1, 2, then we'll do 2, 2, then we'll do 2, 1, and finally we'll do 3, 3, and X was the winner. Okay, and we'll go ahead and assume we tested that verbosely. All right, so that's a version of TicTacToe in Java. Keep in mind that all this bottom stuff is our Rosetta Stone for Java. So this is the entire application with a lot of spaces in there. But makes some decent sense. All right. So what we're going to end up doing, and I'm going to actually start. Let's go ahead and save this back to GitHub. So I'm going to do a git add dot. If I do a git status, you'll see that it notices we have changed driver.java again. It's a new file relative to the local committed repository. So I went ahead and added it. Now we're going to go ahead and commit it. So git commit-m working TicTacToe in HD. All right, and then finally we'll push it up to GitHub. So now it is up on GitHub. There's our working TicTacToe in HD commit. So here's all the code we have currently. All right, that makes some sense. All right, so the next thing we're going to start talking about is string manipulation. All right, so we kind of have the basics down of the Java syntax, translating it from Alice, and we have that primer kind of set up. So now we want to take advantage of some of the flexibility that a language like Java gives us, and kind of the first thing we'd like to look at is string manipulation. That's going to start off. We're going to have to start off by first looking at strings. All right. So in Java, the string data type is just like any other variable. We would say string s is equal to, maybe we say hello, something like that. All right. Now, string has several methods associated with it. And the first two that we're interested in, well, let's say the first one we're interested in, is the length and getting a character at a particular place in that string. So we have two functions. I'll show you the method headers for these. We have int length, takes no parameters, and this guy reports the length as an integer of the calling string. And when I say calling string, this has something to do with the fact that this length method does not have the word static in front. So last time we mentioned that having that keyword static in front of all of our functions, which we basically said we have to have for right now. Okay. This guy says that he is owned by the class in which he's defined. So we're inside the class called driver. Driver owns isWinner. Driver owns play game because it's static. Driver owns make move because it's static. So up here when we called play game, we called it using the name of the class in which it was defined. All right, so let's go ahead and add that one comment in as our starting point for next time. So static versus non-static methods. All right, so we'll leave it at that. We will start talking about this, and we'll have our next homework assignment on Wednesday, due on Friday.